Welcome everyone. I'm very pleased today to introduce you to our very special guest speaker. That's Professor Albert Polman. Albert's from the Netherlands, from the AMOLF Institute. The details are up on the screen there, but it's an institute that I understand is run by the FOM, which is like, as I understand, the ARC here. That's kind of research within the Netherlands. So I think many of you here would already be familiar with Albert's work, but Albert heads a group looking at the application of nanomaterials to photovoltaics. And prior to that, he was actually director of AMOLF, so has had contact with a wider range of issues to do with optical materials. And I think that's been very beneficial to the photovoltaic field in general, bringing a wider range of experience in optics, bringing that to bear into the photovoltaic field. Albert also worked at Bell Labs in the US and at Caltech as well, and has close links to Harry Atwater there, and done a very nice review paper with Harry on the application of photonics to photovoltaics. So without further ado, I'll introduce Albert, who's going to talk on high efficiency solar cell nanophotonic design. Thank you, Albert.
Thanks, Martin. Yeah, so I'd like to review the work we've done in Amsterdam related to light management in photovoltaic materials. And it's a big group of people that was involved, Ph.D. students and postdocs here in my own group in Amsterdam. We collaborate with the Energy Research Center of the Netherlands, ECN, the Technical University in Eindhoven, Philips Research, Helmholtz Center in Berlin, and then a long-standing collaboration with Harry Atwater's group at Caltech. So let's see, where do I switch my slides? This one here. Let's see. Can I do that in a just click? Yes. Okay. So roughly the outline is I want to introduce to you light coupling and trapping using nanophotonic structures integrated with solar cells. Very briefly talk about anti-reflection coatings, nano patterned on glass. Then how we use metallic nanowire meshes as transparent conductors to replace ITO. And then end with a new effect that we have discovered, which we have termed the plasmoelectric effect in metal nanostructures. I'll talk about that at the end. But maybe to start with, this is just a very general summary graph that is taken from the optoelectronic properties of record solar cells of all the, the sort of conventional, the most studied photovoltaic materials that you can find in the literature. So what is plotted here is not the efficiency of all those materials, but what is on the, and that's on the vertical scale here, what is the short circuit current that was measured on each of these materials relative to the Shockley-Queisser limit that you would expect in the maximum efficiency case for that material given its band gap. So that's the current axis, and this is the voltage axis, or in fact the voltage times the fill factor for all these materials. So these are taken from the record efficiency cells for each of these particular materials from the published literature, from Martin Green's tables, from the NREL charts, from other literature. And what this graph shows typically, you could read the vertical scale here as the light management scale, because that's, if the short circuit current is not the maximum value, we're losing current, we're losing light absorption, or there's light reflected, or light in any case is not converted in the active semiconductor material. Or in the vertical scale, we could call, if we don't hit the maximum number here, we have a carrier management problem. So we have recombination, we just don't create the open circuit voltage that you potentially can get. Now that's a little too simple argument, because these, current and recombination and light trapping, they're linked in many different ways. But to first order, you could say, okay, if a certain photovoltaic material is low on the vertical scale here, it has a light management problem, right? Silicon solar cells have very high efficiency, but there's still, several percent to gain here on this axis. Gallium arsenide, the world record for a single junction solar cell, but look how far away this is from the maximum that can be achieved theoretically. So there is light management to do, either in the incoupling of light that is not perfect, in the absorption at some, parasitic absorption in layers where you don't want the light to be absorbed. Cat telluride has a surprisingly high light absorption, but CIGS, for example, is all the way down here. And I don't want to describe all the detailed data points here, but this graph, which is from a review article we're writing, is there to illustrate that yes, on this vertical scale, there is lots to gain for nearly every photovoltaic material. And so I would say in the last 60 years, there's been an enormous progress in photovoltaic materials, which was progress very much also on the material science side, to create new materials with very high electronic quality to get, recombination low, surface recombination low, interface recombination, get the voltage up. At the same time, somehow in some cases, maybe the light part has been a forgotten part. That's certainly not true for all photovoltaic materials. In particular, silicon, of course, has been developed for a long time, in particular here in Martin's lab. But for many other materials, you could certainly say that more attention to the management of the light will certainly help benefit the efficiency. And this is how we, in our lab in Amsterdam, entered the photovoltaics field. After a history much longer ago, when we worked on shallow junction formation photovoltaics in the 1980s and 90s, we didn't focus so much on PV, but we did build up a big program in nanophotonics. And nanophotonics is the research field that tries to understand light at the nanoscale. And obviously at the nanoscale, way below the wavelength, light is not behaving just like ray optics, but it's the near field, it's the local effects of light at the scale below the wavelength that you have to deal with that are completely different than when you just do ray optics. And then we realized if you bring together those worlds of the photovoltaic materials development and device development and new insights from nanophotonics, you may be able to do new things to improve these data points on these both of these axes actually. So as an illustration, as an introduction, what's the sort of concept we want to use here? So if I have this is a cross section through say a solar cell and light would come in from the top. If I put an array of small light scatterers at the surface, they can strongly interact with the light that comes in. In fact, if this is a nanoparticle with a dimension of say 50 nanometer or 100 nanometer, and it can be a metal nanoparticle, but it can also be a dielectric or a semiconductor, then let me draw it here again. If a plane wave comes in from the top, these lines here, these are what's called the pointing flux lines. This is where the energy of the light is going. And if this particle is on resonance, so if this is a plasmon resonance at the frequency of the light at which we come in, or if this is a Me resonance, it's a geometrical resonance with which light is confined within a dielectric particle, then the pointing flux lines will actually focus and concentrate the light inside the particle. So what this graph tells you, the effective cross-section, the area of light that is actually captured by a single particle, is much bigger than the diameter of the particle itself. So the cross-section of scattering can easily be 5 or 10 times bigger than the particle itself. So that means if you have an array of nanoparticles spread over the surface at a coverage of say 10 or 20%, then all the light that's coming in will interact with one of those particles. Now, if you take such a very efficient scattering particle and you put it at an interface between a dielectric and air or vacuum, so let's take here silicon index 3.5 in air, and I put my nanoparticle at the surface. Now if light comes from the top and it scatters from the nanoparticle, it turns out 96% of the scattered light is going in the forward direction, and 4% will be scattered back. Normally, if I have a nanoparticle in air and light would come in, then this Rayleigh scattering will tell us that 50% of the light is scattered in the forward direction and 50% is scattered in the backward direction. But if the substrate is a high refractive index material like silicon, 96% of the light is scattered in the forward direction, and that's because of the high optical mode density in the silicon. So this already tells you that just this simple scattering phenomenon can help you guide light from vacuum, from air, into a high index semiconductor. So that can be done with scatterers at the surface. You can also put your scatterers at the back. So then the infrared light that's poorly absorbed in the semiconductor can interact with those scatterers. And if this is a metal, then the scattering will not go down, but all will go up. But you can scatter the light and basically, if light comes in this way, turn it around and let it propagate in the plane of the solar cell. So in particular for very thin, like CIGS or very thin amorphous silicon solar cells, the layer thickness is so thin, you should look at them as optical waveguides in which light propagates as optical modes in the plane of the semiconductor. And light coming in this way would never couple to those waveguide modes, it would scatter back. except if you put these scatters at the backside, because they can redirect the light and let it propagate in the plane of the solar cell. So, as a first example of that, here's a calculation for if we take a silicon cylinder, 150 nanometer diameter, on a silicon substrate and we shine light on it, then here we can see the resonance spectra. So if I have a silicon sphere here, that's the green line, I can see two peaks here. So this is the scattering cross-section. You see it goes all the way up to 8. So at these two particular wavelengths, we have a resonant mode that we set up in these particles. And for the specialists, these are electric and magnetic dipole modes that we set up that each have a corresponding resonance frequency. This is the magnetic dipole mode and this is the electric dipole mode. Now, so these are called Mie resonances. They're geometric modes where light is sort of confined inside, nearly all the light is inside the silicon nanoparticle. Now if I put the particle on in more intimate contact with the substrate, so now I have a cylinder, so this is a cross-section through a cylinder, so circular if you look at it from the top, and this is what it looks in cross-section. If light comes from the top, it still has a resonance, it still has a Mie resonance, but it's much broader. That's the red curve here. It's broader because the resonance leaks, the light leaks into the substrate, so it's not such a well-defined cavity. So the line width becomes bigger and the cross-section becomes somewhat lower. And actually for a photovoltaic application, that's nice. You have now a broadband scattering effect, a broadband range where the scattering cross-section is well above 1 and light can scatter into the wafer underneath. Here's an example of how you can use that effect. So we have now a silicon wafer that we have covered with these silicon cylinders, and they're again about 150 nanometer in diameter and about the same in height. And then we coated them with a very thin silicon nitride anti-reflection coating, 40 nanometer in this particular case. Now you know silicon, bare silicon will have a reflectivity of 35% or a little higher here in the UV spectral range. Now, if we put our nanoparticles at the surface, we see the reflectivity goes down. That's the red curve here. And if we coat them with silicon nitride, the reflectivity, average over the entire solar spectrum up to the band gap of silicon is 1.3%. So you can see the resonant nanoscattering of these dielectric cylinders help to catch the light and then redirect light in the semiconductor underneath, so that in the end 1.3% is only reflected. You can wonder, how do you make these structures? This is something we initially did in our clean room using electron beam lithography. Of course, that's not a technique that's compatible with large area PV. But now we have this called the substrate conformal imprint technology. It's originally developed at Philips Research by Mark Verschuren, who also did a Ph.D. in our group. And this is a rubber stamp that he developed, composed of 2 different layers of PDMS, a very hard one and a very soft one. And the stamp goes into a liquid sol gel. So if we take the silicon wafer, we can spin coat a liquid silica, so a sol gel at the surface. Then we push the stamp in the sol gel. We let the sol gel dry and we remove the stamp. And so now we have nano-patterned the silicon oxide top layer at our silicon wafer. We can use that as a mask for deposition of metal and do a lift-off process. We can also use it as a mask for etching the wafer underneath. So this is now a large area technique. We can do it on 6 or 8 inch wafers with this rubber stamp, and that means you can also scale this up to a roll-to-roll process if necessary. We have done simulations to see how this light scattering would affect the light absorption and trapping in thin silicon slabs. And this is with the idea that, of course, standard silicon solar cells have wafer thickness of 100 micron, 150 or much thicker. And the question is, if much thinner silicon would become available on the market, could we use these nano-pattern structures as effective light coupling and light trapping layers? And here in numerical simulations we took a 5 micron thick crystalline silicon slab, again with these Mie resonators on top, and then coated them with silicon nitride. And I should say numerical simulations have now become very advanced. So in the nanophotonics research field, numerical simulations, basically solving Maxwell's equations in a complex 3-dimensional architecture, is something we have very good control over, and we can therefore now apply that in photovoltaics. And here's the calculated absorption in the silicon if we had just a flat silicon structure and then for a periodic array of metal or of silicon cylinders at the surface, and then also for a random array of scatters at the surface. So with random, we just, with a random number generator, place the Mi resonators at the surface. The only condition is that they cannot overlap. And then in our simulations, what we see is with the random array, we get a much larger light trapping here at the long wavelength range where the silicon is poorly absorbing. Okay. So why is that? And it turns out that geometry is incredibly important in this light trapping effect. We come in with, if we have a regular array of nanoparticles, we come in at a fixed wavelength and a fixed angle. We can couple well to particular waveguide modes in the silicon slab at a particular wavelength or particular angle. But to couple, to these waveguides modes, that means you have to convert the spatial frequency that you come in with, which is 0 component in the plane, to the eigenmodes of the silicon slab. You can only do that at a limited number of wavelengths or angles. So if you now make the scattering pattern random, you supply a broad range of spatial frequencies that can couple the light as it comes in into the silicon slab. And the trick is to engineer the random array in such a way that the spectrum of spatial frequencies is only covering the spectral band where you want to do light trapping. Right? If we make a completely random structure, it will have spatial frequencies over the entire wave vector range. That's not necessary because in the blue spectral range we don't need light trapping. Light is already absorbed. And since the total spectral density, power spectral density of spatial frequencies is a conserved quantity, we'd better shift away spatial frequencies that would trap blue light and make them more intense in the near-infrared spectral range. So we've been playing in the computer with all kinds of random geometries that these are the spatial geometries, and this is then the corresponding spatial frequency. So this is wave vector here for these particular, all these particular patterns. And then here, this is hard to read, this says spatial frequency, and this is the power spectral density. So this tells you this particular pattern has, a large number of spatial frequencies in this spectral range. This one has it in another spectral range. And now this means that by engineering the random pattern, you can optimize it for the wave vectors that your solar cell, that you need to couple to in your solar cell. Of course, you have to think in the end how you're going to do this in a practical solar cell. You can make these nice structures with silicon and silicon nitride, but a true solar cell needs to be encapsulated, so we also did that. So if we cover this in EVA, a common encapsulant, of course, even then, if we re-optimize then the geometry of this silicon nanodiscs, we can get extremely high absorption in the silicon underneath, as you can see here with the red curve. So the idea with these scatters is twofold. First of all, they catch the light and guide it in the wafer underneath, so they act as a kind of anti-reflection coating. But then the Mi scattering will direct the light over a broader range of angles, so it will also enhance the light trapping. And the question is still an open question we're working on. What is the optimum geometry in which you can optimize both the incoupling and the light trapping? And under what conditions could you overcome the 4n squared light trapping limit in this particular spatial frequency band? You can also wonder, looking back at this graph, okay, if I make a solar cell and I have to make these nanostructures at the surface, I have to pay a big price probably in the voltage of this cell, because there's a lot of area and there's etching, so you have edge damage at the surface. So we wondered, can we just do this differently? So we just took a flat silicon wafer and then we made nanoparticles at the surface not out of silicon but out of titanium oxide. So the way this is done is you take a flat silicon wafer, you spin coat the sol gel, with the rubber stamp you print a pattern in the sol gel, remove the stamp, evaporate titanium oxide, and then do a lift-off process. So now we have titanium oxide nanoparticles at the surface. We have a 5 nanometer aluminum oxide, that's the perfect passivation for this wafer made by ALD. And then and now we have titanium oxide as a scattering layer. Now the refractive index of titanium oxide is 2.2, 2.4, so it's not as high as silicon, so the scattering power is not as high. But if we just do the reflectivity measurements on an optimized coating here, on average we can couple in, we can be left with an overall reflectivity average over the solar spectrum up to the band gap of only 1.6%. Now the big advantage now, of course, is that we leave the silicon wafer intact. It's nicely passivated with the alumina ALD before we put the coating on. And it turns out this whole nano-imprint process does not affect the carrier lifetime in the wafer. So this was a float zone silicon wafer, and after processing with the titanium oxide, the carrier lifetime in the wafer was still 3 milliseconds. So this now leaves us with a solar cell that is flat. So the total area where you can have surface recombination is sort of minimized, right? No texture that enhances the surface area. And we still have a light trapping and light coupling layer at the surface. And since surface recombination, of course, is a dominant factor limiting the VOC, this could be an advantage. And we're actually right now applying this concept on high efficiency silicon solar cells. So the idea is in this case, you don't need macroscopic texture, you don't need chemical processing to make surface texture, but you print the texture that acts both as an AR coating and as a light trapping coating. So then you can dream about all kinds of different solar cell designs where this may work. You could think about a conventional cell where rather than having a flat cell, you put this titanium oxide particles at the surface, or you etch the silicon wafer and then you make sure you passivate it really well, and it's been demonstrated. In fact, you can actually etch these cylinders and also have pretty long lifetime after the right surface passivation. You can think about geometries where you have an IBC geometry, all the contacts at the back, and we use just the TiO2 at the surface and keep the wafer flat so that you have a minimum surface area, etc. Initially, we started the work in this field working on ultra-thin amorphous silicon cells, and now, of course, that's not such a popular material anymore. But it's an ideal model system, and it still is. Because it tells you how these light trapping mechanisms work, and then you can apply them in basically any photovoltaic material system. And so the initial work we did was, this is a amorphous silicon thin film solar cell that was made on a glass substrate where these little black dots, or black cylinders here, are sol gel particles. So flat glass, again, sol gel spin coated, rubber stamp, gave us these nanoparticles here, and then silver was evaporated conformally over these particles, zinc oxide buffer layer, amorphous silicon, and ITO at the surface. And so here is the EQE measurement compared to a flat cell. Of course, in practice you would never make a flat cell. You would take an acai or another type of textured substrate, but this is just for reference here. And what you see is you have a strong enhancement in the photocurrent here, and that's because of the corrugation at the back here. So light comes in at the top. Now it's scattered at these scattering patterns at the back, and then coupled in the plane of the amorphous silicon and propagates as a waveguide mode in here. And we later found, initially we thought that this is all plasmonic scattering because the metal here is like a metal nanoparticle will strongly scatter the light. That is true, but you can see the zinc oxide also as a nanostructure here. So in fact there are Mi resonances here in the zinc oxide and also down there, and they're also resonantly scattering. And it's the combination of those two that actually causes the light trapping. The big surprise we actually saw was that the blue curve here, that's for this nano pattern structure, there was also an enhanced blue response. And that initially we didn't expect because this nano pattern is there to enhance the absorption of red light that's not absorbed in the cell. But of course what you recognize here, this is again the corrugated surface that we saw previously, not the nice silicon cylinders, but for the light it doesn't matter. It's a nanostructure that has an eigenmode. So there's actually Mi resonances in these corrugations at the surface. And they actually resonantly absorb the light and couple it in. So here we again see the anti-reflection effect of this nanoscale corrugation, which enhances the blue response. We collaborated with the Martina Schmidt's group in Berlin, who makes CIGS thin film cells, and this is the typical geometry that she has been working on in her lab. And again, here there's a big light management problem in these thin cells. First of all, the incoupling at the surface was not so efficient, so there was not an ideal AR coating. So we used titanium oxide nanoparticles printed on the finalized CIGS thin film cells. And then here is the absorption in the CIGS in red compared to the flat cell. So there is an enhancement there. And another effect, and we're still working on this, is actually molybdenum absorption in the molybdenum back contact is a serious loss factor too. And so we've printed silicon oxide particles on the molybdenum and then grew the entire cell stack to enhance light trapping. So you get scattering from the silicon oxide and then trapping in the CIGS. And that gave actually quite an enhanced response here in the near infrared. And a surprise we found that actually also the voltage went up on those cells. And that's because we just remove area, CIGS molybdenum interface area, by the SiO2 particles here. So there's just a smaller area from which carrier recombination can occur here at the back metal interface. Also in gallium arsenide, as I mentioned in the beginning, there's still a light management issues that can be solved and need to be solved. So as a model system, we work on rather thin gallium arsenide cells, 500 nanometer and 2 micron thick, and printed titanium oxide particles on there. Now the actual world record cells are much thicker, close to 2 micron. But you may wonder if you could do your light trapping right, you may be able to work with thinner gallium arsenide cells and reach the same efficiency. So this is also something we're working on. And a final design I want to mention to you, this is for thin film crystalline cells, where one of the problems is if you grow crystalline silicon on, say, a textured zinc oxide surface that you need to have because of the light trapping, it's very difficult to grow good crystal silicon. You always have pinholes and grain boundary cracks near the corrugations offered by the zinc oxide texture. Ideally, you want to grow your silicon crystal films on a flat substrate. So what we do here is we take the glass, and the cells is grown from top to bottom here. So zinc oxide, then the microcrystalline silicon. And then at the back side here, we make a geometry where we print silicon oxide particles and then evaporate the silver back contact on top of them. So now we have the flat grown microcrystalline silicon, and the SiO2 nanoparticles here act as the scatterers and light trapping coating. So really, from all these examples I've shown you, we look at the solar cell as an optical integrated circuit, right? It's the same way that you have an optical fiber where light is guided through the core of a silica glass fiber. The core has a high refractive index and the cladding has a lower refractive index. The same is true if you have a submicron thickness silicon or CIGS or gallium arsenide solar cell. And this is a numerical simulation of the light distribution in this particular case, the amorphous silicon thin film cell. So if you shine light from the top, a plane wave comes in, then the color scale will tell you here where the light is sitting. And the more red the color, the more light. So you see this is the contour, this is the amorphous silicon active layer, that's where most of the light is sitting. There's still some lights in these resonant modes here in the ITO at the surface. Okay, so that's bad news because that'll be parasitic absorption. There's also light here at the back in this zinc oxide and at the surface of the silver. So silver is a metal. It's not a perfect metal, so there's a skin depth of 10-20 nanometer, and you see there's light penetrating into the silver there, and it's also not what you want because it's also absorbed. So these kind of numerical simulations will tell you exactly where the light is sitting, and it also means you can engineer your cell in such a way that you get sort of optical hotspots in those regions where you can easily collect the current. As a little side experiment, little intermezzo, we figured we could use this nano-imprint technique also to solve something very simple, namely any solar cell is encapsulated in glass, and glass has a refractive index of 1.46, so you get a reflection, 4% reflection. And of course you can avoid that if you put an AR coating, but the AR coating then needs to have an index of about 1.22. There's no natural materials that have that index. So we thought, let's make that. So we took the sol gel, printed with a rubber stamp, and made what we call the nanoglass coating, which is basically an effective index coating. So the particles are much smaller than the wavelength of light, so just the average volume fraction of the nanoparticles will determine what the effective refractive index is. And so you see an SEM image of these small silica discs. This is a 100 nanometer scale, so this is a roughly wavelength scale, and the effective index is 1.22. And we can print it at extremely large area. And then we measure the reflectivity, which on a flat glass slide from two sides is 7.3%, so reflection from top and bottom. And this is a classical AR coating curve, for this two-sided coated glass nano coating. 1.1% average reflectivity. We've actually done this on small encapsulated silicon solar cells, encapsulated in glass. And here you see the typical glare, 4% reflection. And here the same cell if it's covered with this nano imprint. And with a corresponding increase in the photocurrent as expected. If it works on solar cells, it should also work on smartphones, which have the same problem, right? A big problem if you want to read something on your smartphone in the sun, you have this 4% reflection, or even more if it's made out of alumina. And so here, it's hard to see, but this is sort of the reflectivity of the smartphone taken with a picture, reflectivity of the lighting in the ceiling. And if we pattern the cell, that effect is much smaller if we pattern the phone. So here we just bought a replacement screen for an iPhone to do this experiment on. And it demonstrates you we can just, with a rubber stamp, just easily imprint an entire screen. Now, in my cartoon at the beginning, I showed you these these resonant nanostructures that will, interact with light and then guide it in the wafer and then get the light trapped. And we initially got into this field because of plasmonic nanoparticles, because there was a new area in nanophotonics that came up, and also, nanoparticle sizes and geometries could be controlled very easily in using clean room techniques. And it got us, working in this area. Now, a big disadvantage of the metals is that they're lossy. Right? They scatter efficiently, but there's always parasitic absorption. That is why in many of the examples I showed you before, we've made the switch to these dielectric scatterers. So a silicon particle will scatter light as efficient as a metal or silver nanoparticle, but it does not have the parasitic absorption. However, there's of course one big advantage of metal, and that is it's an electrical conductor. So you could imagine that you have a nanostructured surface with metal nanoparticles that act as the light scattering and trapping layer, but now you interconnect them to make an electrically conductive grid. So now you have a transparent conductor. Transparent because light will interact with this metal nanostructure, it will be scattered, and it will be preferentially scattered forward into the wafer. That light doesn't care if it's nanoparticles, is it wires, if it's interconnected wires. It's nanostructures, it's resonant nanostructures, and light will interact with them and scatter. So it's transparent for light, but it's also a sheet that will conduct electricity. And so we initially made this with the electron beam lithography. Here are our grids. They're 65 nanometer wide silver grids that we printed here on glass and on silicon. And then we did optical transmission measurements. So here is transmission as a function of wavelength. And the numbers here are the wire width. So this is a 110 nanometer silver wires. This is 45 nanometer silver wires. And so obviously if we make the wires very wide, the transmission is bad because there's a lot of absorption in the metal. But if we make them narrow enough, actually the transmission can be here higher than 80 or even 90%. And this graph is quite complex because you see several different features. You see a big dip here, you see a smaller dip here, and then also here appears to be a dip in the near infrared. This graph tells us what the fundamental scattering mechanisms are from these nanowires. First of all, the big dip here is because light comes in and interacts with a wire. So here's the metal wire, light comes in, and the light that's polarized in the perpendicular direction will set up a plasmon resonance in the wire very efficiently. And that light is partly scattered and partly absorbed in the metal. And so the big dip we see here is because we set up localized plasmons in the wires. Now, wires can also guide plasmons. They're little leads of electromagnetic energy, and the plasmons can propagate along these wires. But only if you match the wave vector mismatch between light that comes in this way and the wave vector of the plasmon. And that's done by the grating that is supplied by this regular nanopattern. So the regular array of wires just will help light make the turn and couple to these propagating plasmons along the wires. That's this dip here. Propagating plasmons. And then there's a big gap here, a big dip, and that's because if you have two wires, then you can squeeze light in between those wires. It's called a TE, a polarized mode that can propagate in these wires, it gets absorbed, and that is a big dip that extends here in the near IR. And it's important to understand all these scattering mechanisms, because if you understand them, you can try to get rid of them. Right? You can vary the pitch, you can vary the wire width. Maybe you want to get away from the square grid, you want to make a random grid, and all these design efforts can be made to move away these big dips away so that in the spectral band that you're interested in, light is effectively transmitted. We've done IV measurements and measured the sheet resistance of these metal nanowire grids, 17 ohm per square, 2738, depends on, of course, on the pitch of the wires. And these are typical values, very similar to those of ITO, depending on the thickness and the kind of ITO. So now we can play with the wire pitch, so the distance between the wires, and the wire diameter and the wire height, and basically move on this graph. This is transmittance and this is resistance. So we can make the wires very narrow so that they transmit a lot of light, but of course the further we go this way, the higher the resistance. And so we can just pick, we can pick the combination of transmittance and resistance that we want for a particular solar cell and make a metal nanowire grid. So overall, we think in particular conditions, and I'm going to show one here, that we can design these nanowire grids in such a way that they can be better than ITO. And of course, ITO is something we'd like to get rid of, right? It's expensive, it's brittle, it has indium, which is a rare element, it's absorbing in the UV. So here we're investigating what happens if we take a heterojunction solar cell with ITO at the surface and we take away the ITO and then add silver nanowires. So this is a CZ wafer with the thin amorphous silicon at the surface to make a heterojunction cell, typically 80 nanometer of ITO and then silver fingers at the surface. And now we're going to put silver nanowires on the top. And here you see SEM images of wires with 80 nanometer width, varying pitch here. We can also vary the wire width. And now what's special about these ones, these are all made by soft-imprint. So no e-beam lithography, no expensive clean room technology. Again, sol gel, print your structure, evaporate metal, and there you are. So large area nanowire grids, you can see it. These are an array of grids printed on a mechanically polished float zone silicon and a chemically polished Jagrodsky ground silicon. These had completely different surface textures, and we were interested to see how conformally we can actually coat these with the nanowires. So if I take a polished float zone silicon wafer, then this is an AFM. So each of these peaks here is a nanowire. Right? So the nanowire height is 50 nanometer, they're equally spaced, and it's going very well on a flat surface. But on a chemically polished rough CZ wafer, height variations of 100 nanometer, you can see I can conformally with my rubber stamp put these nanowires at the surface. And so what we've now done is we've taken the cell design with the 80 nanometer ITO there and now replaced the 80 nanometer ITO with nanowires, but we kept 20 nanometer of ITO underneath. We found that was essential because we want to have like a chemical buffer layer for all the processing we do with the wires. So the ITO acts as a chemical buffer with the high quality silicon underneath. And also the plasmon resonance in these silver nanowires is shifting away. If we put them on silicon, it shifts too far in the infrared, and actually that puts us in the wrong spectral range. ITO has a lower index, so it moves away the plasmon absorption to the UV spectral range. And so here you see the cells, they're 2.5 by 2.5 centimeter. So this is strange cells, they're flat silicon heterojunction cells, right? So they're not textured. So they have an efficiency of about 15% because they're not textured. But this was sort of as a reference because it helps us compare. So flat cell, these are the bus bars and the fingers, and with ITO, and then taking away most of the ITO, and now between the fingers we have nanowires with a pitch of 1 micron, 2 micron, or 4 micron. You see it from the different interference colors over there. And so then we measure the IV curves. For the no nanowire case, we have an efficiency of 15% here. This is the fill factor. Here's the short circuit current. There's the voltage. And now we're going to add wires and space them at 1 micron. Now if we space them at 1 micron, then we lose a lot of light because of absorption in the metal. So we pay a price in the current. Right? Fill factor goes up, of course, because we have much lower series resistance now. Right? But the current went down. Now that means we have to put these wires further apart, 2 micron and 4 micron. And it turns out, so this was 1 micron, 2 micron, 4 micron. So short circuit current has gone up very close to the value for ITO. But you see from the curve here, the fill factor has significantly improved. And it turns out that in the end, the efficiency for this flat, heterojunction cell is 16%. Here's the reference with 20 nanometer ITO, and the 80 nanometer ITO was here at 15.1%. Oops. So yes, these nanowire grids for this particular design, they can actually replace the ITO and be transparent enough and conductive enough, even for this high current HIT cells, to improve the ITO case. Now, as I said, this was a flat heterojunction cell. Normally you would never make that. You want to have a textured cell. So here is just as an example. This is a textured silicon wafer with the metal nanowire grids printed on top. So these are silver grids that are printed on top of this textured surface. So this particular textured surface we made by taking a flat cell. With our soft-imprint technique, we made a grid of copper wires. Then we did KOH etching. Right? So originally, here on these ridges, that's where the copper wires were that acted as an etch mask, and then you make these perfect inverted pyramids. So here's the scale, 3 micron. We remove the copper, and now we spin coat the sol gel. We print the stamp, remove it, evaporate silver, and this was this surprisingly conformal coating of silver. If you look at it in detail, it perfectly coats the slanted edges here of the inverted pyramids and makes a perfect conducting network. So of course that's the next thing we're doing right now on these heterojunction cells. Let's see if we can apply them there. I'm coming to the end here, and I want to very briefly tell you about something completely different that we discovered. This is the collaboration with the Harry Atwater's group. The plasmoelectric effect, an entirely new way to generate a photopotential without using a semiconductor. This is a way to convert light into voltage using only metal. And it's based on this very simple concept here. If you have a metal nanoparticle on a grounded substrate, and you want to know what the plasmon frequency of that particle is, it's this simple equation. It's the carrier density, and there's the effective mass here, but the carrier density, it counts. So if I have a silver nanoparticle, then the carrier density in that nanoparticle for silver is known, and I can just calculate what the resonance frequency is. The equation also tells you if I would be able to increase the frequency, or increase the carrier density in a nanoparticle, the resonance would shift. Right? So if here it's in black is the resonance spectrum at a certain wavelength. This is for a silver nanoparticle in air. If I would add 2% extra electrons to that single nanoparticle, it would shift a little bit to the blue because of this equation. Right? The frequency goes up. So that would be the blue resonance spectrum. Or vice versa, if I was able to take away 2% of the electrons from the gold-silver particle, its resonance would shift to the infrared. Now, let's see what would happen. If I shine light on this nanoparticle of resonance, say at this particular range here. Here's my silver nanoparticle, and I shine light on it. Now, let's assume what happens if I add one more electron. Then the resonance will shift to the blue. That means the absorption cross-section is actually going up. Right? So if I sit at a fixed frequency, and the black curve was my starting point, and now I add 2% electrons, now the cross-section goes up a bit. If the cross-section goes up, I absorb more light. If I absorb more light, the temperature goes up. Right? That is thermodynamically favorable because it raises the entropy of the system. So at a fixed wavelength shining at this silver nanoparticle, if I would just add one electron, and statistically of course electrons go back and forth, adding that electron is thermodynamically favorable, right? Because it in the end will raise the temperature. But at the same time, adding an electron costs electrostatics, right? There's an electrostatic potential that you build up, so there's a energy penalty there. So in the end, the system will find a new equilibrium. It will slightly charge up, so it can raise its temperature, but it will do it to such an extent that the energy gain by the entropy associated with it is equal to that of the energy lost by the electrostatic charging power. And that mechanism we can work out in this thermodynamic equation. I won't go into the details here, but it's just what I said. There's a chemical potential associated with charging up. There's an entropy term. And what is very important here is how does the temperature of the nanoparticle depend on the carrier density? This function, and that's intrinsic to the shape of the scattering spectrum. This function will then eventually tell you how much charge you can in equilibrium build up in a nanoparticle. So it means if I have a nanoparticle and I shine on the blue side of the spectrum, it will charge up with electrons. If I go to the other side of the resonance spectrum, it will actually release electrons. And that works. You can see in this graph. This is silver nanoparticles on ITO. And this is a scattering spectrum. And here's now, we take a Kelvin probe microscope. It's basically an STM where you probe over the surface and you measure the potential over each of these particles. And we do that for different illumination wavelength. So we come with monochromatic light, and the resonance you can see here is at 560. So if we are on the blue side of the resonance, what we see, we have a negative surface potential, and if we're on the red side, we have a positive surface potential. Now these were pretty difficult experiments to do. You can see also from the data, it's not very smooth, and ITO and silver nanoparticles, and they oxidize, and so in the end, we went to a structure that looks like this cartoon. We just took a metal film. So rather than using metal nanoparticles, we made the inverse structure, a metal film with holes. And that also has a resonance. Because light will come in, scatter from these holes, form surface plasmons that propagate over the surface. They will scatter back and forth between the holes. And the distance between the holes then determines the resonance. So the same way as metal nanoparticles have a clear resonance spectrum, as you see here, also a metal film with holes will have the same resonance, and therefore the same principle should hold. And indeed it does. So here's an SEM of a silver film, 500 nanometer is the scale here, so 250 nanometer pitch. Light is shining on these particles, generates plasmons that propagate back and forth, that generate a resonance. Here's the resonance as absorption spectrum for one particular pitch. If you put the holes further apart, the resonance will shift into the infrared. And here's the key measurement. Here's again the surface potential. We take this sample here. If we shine on the blue side, we get a here's the data more clearly. If we go on the blue side, we see a negative surface potential, so charge is added to the particles. If we go to the red side, we see a positive potential. And if we do this on different samples with different resonances, you see this effect will systematically shift with geometry. So this is an entirely thermodynamically driven effect where light comes in and generates potential at the surface. Now we don't have a current yet, so this is not a solar cell that generates power. We have voltage. But to create the voltage, we have to have current that flows back and forth. So the current is there. And so the next step we're doing now is building very small integrated circuits where we try to raise the voltage and create a product with the current so we have power. So with that, I want to end to summarize that I talked to you about light coupling and trapping using resonant nanostructures at the surface that help trap light in ultra-thin solar cells like amorphous silicon or CIGS. In fact, it's generic to any thin photovoltaic material. But it could also be interesting on thick wafer-based silicon cells, or maybe the thinner wafer-based cells going down from 100 or 50 or even thinner, where maybe the chemical polishing is more difficult to do, and it could be interesting to just imprint the texture at the surface. The same concept was used to make AR coatings on glass, and then I introduced to you the metal nanowire grids that can replace ITO, and briefly showed you the new plasma-electric effect in metal nanostructures. And with that, I want to conclude, and thank you for your attention.
Yeah, we've got time for questions, so I assume you're happy to take
Sure, of course.
questions.
Yeah.
So, yeah, thanks.
Thanks, Professor Polman, for your very inspiring talk. I'm very interested in your plasma-electric effect. Have you thought about the combining with the nanowire network you've done?
Yeah.
I mean, probably you have the plasmonic effect in your nanowires, and will this kind of resonance affect the conductance, for example, of the wires?
Yeah. Yeah, in fact, one of the initial series of experiments we did was with the nanowires, and it was in fact because we were working on these nanowire coatings that we thought, that concept could work for plasmaelectrics also, after it also worked on the colloids. Fundamentally, there's not a big difference. Going from a wire to a thin film with holes, plasmonically, it's just a matter of geometry. So, Yeah, you solve Maxwell's equations of the modes. Sometimes they're propagating modes, sometimes they're localized modes. And in reality, it's all the same. So I guess it's about engineering the cross-section. When is that best? Maybe for a film, we get a higher cross-section for the nanowire grids. I think at the end it will depend on your application. But for now, there's not a fundamental difference.
But I mean, the application of the nanowires, you have like sort of constant flow of the current, and you have a kind of plasmonic, like this kind of resonance movement.
Right.
So will it actually affect the constant flow of the current?
Right now, the plasmoelectric effect is a very small effect. So the kind of currents associated with charging to these individual structures are extremely small. They're much smaller than the current you would draw in a solar cell.
Thank you. The second question is, if you have a finger like this, I don't think you really need a grid like this, right? You only need the sort of one dimension.
Yeah, you're totally right. So we were a little modest that maybe in the fabrication there was a risk that some of the wires would break, and then of course you lose. But turns out the nano imprint is so reliable, we could just do with the parallel wires. Yeah.
Just a question on the nanowire. Thank you for your interesting talk. Just wondering, did you try random nanowires as well?
No. You mean for the metal nanowires? Yeah. No, and that could be advantageous because then you can play with the spatial frequency density. It has been done for chemically sensitized nanowires that are made in solution and then sprinkled over the surface so that you get a random grid. And that is a cheaper process, but you have less control over the dimensions. So in the end, I think optically it's much better to do it in a printed fashion, but maybe random is better.
Thank you for the presentation. My question is, have you worked on the thickness of ITO, the 20 nanometer? You told us about that. Have you worked on the thickness of the ITO?
Yeah, right now we use 20. One question is, can you make it? How thin can you make it? So if we make it thinner than 10 nanometer, then the metal nanogrid will start to feel the silicon underneath. So the plasmon resonance will shift the wrong way. So I think 10 nanometers is a kind of minimum. As I said, it's also there as a chemical buffer for everything of the processing we do. That probably would work for 10 nanometers as well. So maybe we can go a little thinner.
Have you think to, get rid of totally get rid of ITO or not?
Sorry,
I mean, any replacement of ITO. You don't need, I think, the ITO.
That's right. So we could put something else underneath that is just there as the chemical buffer, and that it needs to conduct, of course, from the wire to the wafer underneath. But it does. You're right. It doesn't have to be ITO. Yeah.
One of your early slides showed absorption enhancement at 5 micron thick silicon.
Yes.
We usually, when we're showing something similar, compare it to the best silicon solar cells of various thicknesses. I think if you did that, you'd find they all had substantial absorption and conversion at 1100.
Yes. Okay. So I guess this is for a 5 micron slab. Is that also what you're referring to?
Yes.
Yeah. Okay. Well, I think we did rough calculations that predicted that for this particular cell we could get an efficiency of 22 or 23%. And
maybe a different question. Do you calculate an effective optical path length?
not in this particular case. Here we numerically look at the total light absorption in the active layer. Yeah, but maybe you're saying we should plot and compare to the 4n squared calculation for this particular thickness. Then we're getting pretty close, but we're not exceeding it.
Too bad.
Yeah, but there's no fundamental reason why we cannot exceed it. So I think by
we all hope that's true.
no, but yeah. So that this random engineering by playing with the spatial frequency range, I think it should be possible to exceed 4n squared in a certain spectral band. You pay a price in another spectral band.
Okay.
the subject of random.
Maybe you got 3 more questions. So
Go on.
1, 2, 3. Ivan, you're first.
Oh, fancy one.
I was interested. I suppose all the measurements that you've done are with normal incident light, right? So is this a very broad angle of acceptance? Because in the end, we care of how much energy we harvest.
Yeah, yeah. So that's where the random patterns come in. So if you do a random array, you can make it such you can catch a broad range of frequencies of a large angular range. The same is true for our anti-reflection coatings on glass, for example. Yeah, they work on, over a broad angular range in a similar way, and standard AR coating would do that.
In the beginning, you showed the plot of record efficiency cells and the opportunity for improved light management. Has nanophotonics contributed to any of those records?
No, it hasn't, and that's a very good point, of course. So none of the sort of nano-imprinted structures I showed you so far have done that. But it shows you, how small steps we all need to make. So
what's been the downside?
I could imagine, for example, in the CIGS cells, where there's a lot to gain in light management, actually a properly designed nanostructure could help. I'm still curious about the thinner wafers. If you have a 50 micron thick wafer by nano imprint, less surface area, less surface recombination, is there an option to do so? So, yeah, as always in these kind of research areas, you make small steps and you hope to at some point find a material where you can really make an impact.
Okay, 1 question there. Okay, we'll send it to 2 more. Next
I wanted to
question.
ask about the arrangement of the particles on the surface. You're looking at mostly random and just square arrays. Have you looked at other engineered arrays, sort of periodic or quasi-periodic?
No, so far not. So, except with random, in the amorphous silicon case where we looked at the spatial frequencies, there we engineered the degree of randomness. So we start with a random number generator for x and y coordinates, and then we displace particles and we measure the spectrum of spatial frequencies, and if it gets better, we keep the particle there and we displace another one. So then in the Monte Carlo technique, we engineer the degree of randomness.
And sort of connected to that, have you found like there's a good balance between, say, like the waveguide coupling from that spatial arrangement versus the scattering? Do you find like sort of you prioritising one over the other to get the optimal?
The scattering in terms of the incoupling, you mean? Or
There's like a balance between the 2 effects, effectively,
Yeah.
like the waveguide coupling from the periodic or random.
Yeah, so they're they're integrated in the numerical simulation. It's hard to distinguish the two because we just measure the overall absorption in the film. So they're combined.
Okay, last
Yeah, that was more or less my question. I guess we seem to switch from absolutely periodic, either hexagonal or square, all the way up to random. Are there opportunities with quasi-periodic or long-range order or chiral, to use a word from my past, chiral asymmetric structures, really? I mean, it seems that there hasn't been a lot of work in those areas up until now.
Yeah, or even as weird as these that turned out to be really promising structures because they have a very narrow spatial frequency spectrum here. So, yeah.
We have quite a narrow area of concern around the band edge for most systems, I guess. Yeah. Seems opportunity there.
So these are the kind of structures that you need to worry about then. Yeah.
Okay, thanks everyone for their questions, and thank you Professor Polman for an excellent talk. Will you all join me in showing our appreciation?
Thank you.